It's day 18 of 50 days of tutelage, and today we'll be talking about mole concepts in our chemistry class. So before I get into the chemistry of mole, let me talk about what a mole is. The first thing you need to know is that, so loosely, let's define mole. A mole, the perfect way to define it is that it's like a packet. It is like a packet of elementary units. Elementary units of matter. So that is the best way to describe what a mole is. It's a packet, that is, it's a collection, it's a pack of elementary units of matter. I'm going to be giving so many details about this later on. So what do we really mean by this packet of elementary units? I know you are familiar with statement like a pair of something. So a pair. Now a pair can easily go with a pair of shoes. You can have a pair of socks. You can even have a pair of kidney. Yeah, you can have a pair of kidney. And then you can have that of arms, legs, and all of those. Those things always come in pair. So the moment you mention that a pair of something, the next thing that comes to your mind is that you're going to have two of those things. You're going to have two of those things. Once you mention that we have a pair of something, we're going to have two of those things. It does not matter which one is heavy. It does not matter the nature of that thing. It does not matter which one is lighter. But once you mention a pair, what comes to your mind is what? Is how many of those things are going to be there. So you begin to see that when we talk about mole, what should be coming to your mind is actually about how many as well. Another one is dozen. So if you have a dozen of eggs, or you have a dozen of arts, yes, like several arts in the same place, so you have a dozen of those. The next thing that comes to your mind is that you have 12 of those. So you have 12 of this and you have 12 of this as well. The same thing with the mole as well. The mole, I'm going to refer to that loose definition I gave again. It's a packet of elementary units of matter. So what is now going to be the best way to describe a mole? One last thing before I give the chemistry definition. I know most of us were familiar with rice. We're familiar with rice and we are familiar with millet. Rice and millet. These guys, they look actually like closely together. They look almost the same thing. Now, what is, let's assume that one grain of rice has a mass of, let's say, 2 grams now. 2 grams. And then 1 grain of millet has a mass of 3 grams. By the way, what I'm doing here is not a perfect example, it's just illustration, more like an instructional material to just explain something to you. So don't take it as I'm going to be saying it like that. So if we assume that for each grain represents one atom. If each grain represents one atom, what the mole concept is trying to say is that the number of grain of rice or the number of grain of millet that will be present in a given mass, as long as this mass, when you break it down to the simplest form, the mass is always going to return back to this. It's always going to return back to this. Then they will always contain the same amount of grain, the same number of grain. For example, if I say 20 gram of rice, so I don't need to count it. I just carry on a balance. I just measure 20 gram of rice. I don't need to count the number of grains that are there. Then I also measure, let's say I measure 30 grams of millet. Another one, let's say I measure 10 grams of rice and I measure 15 grams of millet. Let's do one more. Let's say I measure 16 grams of rice and I measure 24 grams of millet. So the mole concept is telling us that if you measure these things by mass, even though this one is 20 gram, this one is 30 gram, these two, they're going to have the same number of grain of, this one will have the same number of grain of rice as it is the same number of grain of millet here. So if there are 2,000 grain of rice in this place, there will be 2,000 grain of millet as well. The same thing with 10 and 15, the same with 16 and 24, because when you compare them to what the mass of one grain is, they are just multiple. Like this one is just 2 times 10, this one is 3 times 10, this one is 2 times 5, this one is 3 times 5, this one is 2 times 8, and this one is 3 times 8. So whenever you measure the mass like that, so which now brings me to definition of mole. So what is a mole of an element? What is a mole of an element? So a mole of an element will be the collection, a collection of its atoms, a collection of its atoms, such that when you weigh this collection, that mass will correspond to the relative atomic mass of the element. I'm going to take that again. So what we say a mole of an element now. So if you pick, let's say, sodium now, and you say a mole of sodium, the relative atomic mass of sodium is 23 grams. So when you pick a mole of sodium and you measure it, the weight of that mole is going to be also 23 grams. And the thing is that there is a number of atoms that is contained in this whole thing. And that number of atoms that is contained in 1 mole. So whenever you say 1 mole, the number of atoms that will be there is 6.02 times 10 raised to the power 23. This is what you call the Avogadro's number. Avogadro's number. So this implies that whenever you pick guys like sodium, you pick guys like potassium, you pick guys like phosphorus. Now, even though these 3 guys, they have different mass numbers, but when you pick 1 mole of each of them one mole of each of them, you're going to have 6.02 times 10 raised to the power 23 atoms in each of them. I want you to take note. Sodium, potassium, and phosphorus. Remember when we were doing atomic structure, and then we had said that, so let's pick sodium for example now. Sodium has 11 protons in it. So we have this, let's say this is the inner shell, the K shell, we have the L shell, and we have the M shell as well. So we know that from the inside, you have 2 electrons here, 1, 2. You have 8 electrons here, 1, 2, 3, 4, 5, 6, 7, 8. And that's 10. So now the 1 electron is going to be here. This is just 1 atom. This is just 1 atom. So what we're saying is that inside 1 mole of this, 1 mole of sodium, there are 6.02 times 10 raised to the power 23 of this guy in it. So meaning that if you measure 1 mole of sodium now, the atoms you can pick as much as these atoms here. Now this is a number that is going beyond millions, trillions as well. It goes like way beyond trillions. Meaning that you can pick one after the other. So let's assume that this number is 6. Let's forget about the index of 10 that is behind it. So let's say this number is 6. So what we're saying is that when you measure 1 mole of sodium, you are going to get 6 of this. That is this structure now. You're going to get 1, 2, 3, 4, 5, 6 of this. But it's not 6. I just use 6 so that you can get it. We are going to have 6.02 times 10 raised to the power 23 of this. And that is just 1 mole of sodium. But that 1 mole of sodium, the mass number is going to be what? Is going to be 23 grams. So going back to what I defined now, a mole of an element. So a mole of sodium now is the collection of its atoms. What is the collection of these atoms? That the mass of that collection is going to be equivalent to its relative atomic mass. So now we can link it up now. So 1 mole of sodium, what's the mass? 23 grams. How many atoms does it have? 6.02 times 10 raised to the power 23 atoms. So collection of 6.02 times 10 raised to the power 23 atoms gives 1 mole of sodium, and that weight is 23 grams. Now, for phosphorus, the atomic number of phosphorus is 15, and its mass number is 31. So look at this now. If you draw for phosphorus, we have this 1, 2, and we have 3. So we have the third shell. So in the inner shell, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Now, this is one atom of phosphorus. So what we're saying is that when you measure 1 mole of phosphorus, 1 mole of phosphorus, it contains 6.02 times 10 raised to power 23 of these guys. This is the number of atoms that are present in phosphorus. So every single one of these, like you pick it one after the other. Another thing we're trying to say is that the number of protons in one atom is 15 protons. It implies that the number of atoms that will be, sorry, the number of protons that will be in a mole of phosphorus now will be 15 times this. This times 15 will be the number of protons that will be there. Now, what will be now the weight of this guy? The weight of this guy is 31 grams. So let's go by what we did for, in the case of sodium. 1 mole of sodium, it weighs 31 grams. But it also contains 6.02 times 10 raised to the power 23 atoms of phosphorus. So the same way 1 mole of sodium weighs 23 grams, but it contains 6.02 times 10 raised to the power 23 atoms of sodium. The same way 1 mole of phosphorus weighs 31 grams, different masses, but it contains the exact number as well. So that is why earlier I defined that mole is like a packet of elementary units of matter. So it is not about the nature, it's not about the type, it is about the number. So mole is a form of counting system in chemistry, and you've seen the model of counting. So that is the introduction to what the mole concept is. Now, this cannot be related to so many other things because I may not necessarily need 23 grams of sodium. I may have 5 grams of sodium. I may have 6 grams of phosphorus. So how do you now do all this calculation? How do you know the number of atoms that are present? How do you know different things? Now, we have some different formulas that govern this whole thing. We have number of mole. The first one we're going to be doing is mass divided by the molar mass of the substance. Now, what is mass? What is molar mass? Mass is how much an object weighs. So if you weigh an object now, so let's say this is a random element, and I weigh this thing on the balance, it could weigh, let's say, 50 grams. So that is how much it weighs. This same guy, I can cut it into maybe two halves, and one half is going to weigh 20 grams, and the other half is going to weigh 30 grams. So it is still the same substance, it has not changed. But when we say molar mass, from the way the name sounds, molar mass, we're talking about the mass that corresponds to 1 mole. The mass that corresponds to 1 mole, meaning that in this case, n is going to be equal to 1. So in this n equals to 1, then you realize that if you cross multiply, mass is going to be the same thing as molar mass. So what we're saying is that whenever you measure this mass of this substance, and then this mass corresponds to 1 mole, then that is actually the molar mass of the object. So molar mass is the mass of a substance that corresponds to 1 mole of it. 1 mole of a substance, when you measure the mass and you have a certain mass, that mass is called molar mass. And that is why molar mass is given as gram per mole. The unit of molar mass is gram per mole. So the first relationship is number of mole is mass divided by molar mass. So for sodium now, number of mole, if you measure 23 grams of sodium, its molar mass is also 23. So therefore, 23 grams per mole. So therefore, the number of mole is going to be 1. But you know you can easily do 5 grams, you can usually do 7 grams, you can even do 17 grams of sodium. And then you can get the number of moles that are present in it like that. That is how many packets. That is why you can go and say 2 dozens, 2 pairs, 3 dozens. Because now you are counting in numbers of 12 yeah, for dozen. So 2 dozens, 5 dozen. You know that when you have 5 dozens now, each dozen contains 12. So therefore, you have 60 of it in it. The same thing we can say 2 moles, 3 moles, 4 moles, 5 moles, and so on like that. And then there is something I want to quickly like show you. I had said already that if you have 1 mole of, okay, let me go back to this. 1 mole of each of these guys, sodium, 1 mole of this, 1 mole of this, they will always contain the same number of atoms. But there's something I want to tell you. What if we reverse engineer the process and we give the same mass of all of these guys? So let's go back to sodium. Sodium, potassium, and phosphorus. This one is 23. Potassium should be 40. And then this one is 31. So those are their atomic masses. So let's say, for instance, I give you 2 grams of sodium, 2 grams of potassium, and I give you 2 grams 2 grams of phosphorus. So you now want to know which one of these will contain more atoms, which one of these will contain more particles. The way to do that is that if you look at this now, you realize that if you begin to find the ratio, that is number of moles. Number of mole is, in the case of sodium, it will be 2 divided by 23. In the case of potassium, it will be 2 divided by 40. In the case of phosphorus, it will be 2 divided by 31. Now, if you find this ratio now, you notice that this one will give the highest value. Yes, the one with the smallest denominator will give the highest value. Then it follows by the next one, that which is 31. So next highest. So let me use small h. And this one will give the smallest value there, which is going to be this. So that implies that the number of moles of sodium that you have in 2 grams is actually more than that you have of potassium, and more than that you have of phosphorus. So therefore, these 2 grams of sodium is going to contain more atoms than phosphorus, than 2 grams of phosphorus, and than 2 grams of potassium. I believe that makes sense to you because the number of mole is higher, therefore there will be more particles present in it as well. By the way, this is between 39 and 40, so I don't know that offhand, so you can just confirm it. So let's proceed. I've given one formula for number of moles, that is mass divided by molar mass. There's also another one. I've been talking about the Avogadro's constant since. So number of mole can also be regarded as number of particles divided by 6.02 times 10 raised to power 23. And this particle can be the number of atoms. I think I've dwelled so much on that. And this one can be molecule. And it can also be the ions. So now, let me explain this quickly. If you have number of moles and then you're looking for number of moles and you're given the number of molecules, 1 mole of hydrogen gas rather, 1 mole of oxygen gas, and 1 mole of hydrogen gas. So inside each of this 1 mole of hydrogen gas or 1 mole of oxygen gas, how many molecules are present in them? It's just simply 6.02 times 10 raised to power 23 molecules. They are present in 1 mole of hydrogen gas. But however, how many atoms will be present there? Because per molecule, you have what? You have 2 atoms of hydrogen there. So therefore, you are going to have, since in 1 mole, you now have 6.02 times 10 raised to power 23, then you are going to have what? You're going to have 2 times 6.02 times 10 raised to power 23. So, for instance, if I'm given a question, and then you are asked that, given a certain mass of oxygen gas, so a certain mass of oxygen gas, let's say the mass is 5 grams. So you are asked to find the number of atoms that are present in this. So to find the number of atoms that are present in this is what you're going to do. The first thing is that in 1 mole of this, so number of mole equals mass divided by molar mass. And so that is going to be 5 divided by What's the molar mass of oxygen gas? That is going to be 32. So what is 5 divided by 32? 5 divided by 32, that is going to be 0.156. Now that we have this, so 0.156 mole, that is this. You now use that number of mole equals number of particles divided by Avogadro's constant, 6.02 times 10 raised to the power 23. So what that implies is that you're going to have number of molecules is going to be 0.156 times 6.02 times 10 raised to the power 23. And so whatever result that you get here, let me quickly multiply that times 6.02. So that is going to be 9.41 times 10 raised to the power 22 molecules. But inside this particular guy, there are 2 atoms of oxygen there. There are 2 atoms of oxygen per 1. So therefore, the number of atoms here will be this multiplied by 2. The number of atoms there will be this multiplied by 2. So the next thing we want to do, I want to give you more. I've given you like 2 formulas for finding number of moles that relate number of moles and different things. Now, of course, don't forget to do this yourself. You can multiply this by just multiply it by 2 and then you get your result. So let's go forward. Number of moles can also be given in terms of concentration multiplied by volume. Concentration of a substance multiplied by its volume. Of course, this one we'll talk about it better when we get to stoichiometry. Another thing is that number of mole can also be given in terms of, this one is only for gases. So it can be given as volume in dm cube divided by 22.4 dm cube. Why? Because this 22.4 dm cube is the volume that a gas will occupy at STP. Is the volume that a gas will occupy at STP. So noting that this formula is used for gases at standard temperature and pressure. So volume in dm cube divided by 22.4 dm cube. Or if you are using it in cm cube, this 22.4 will be 22,400 cm cube. It will be 20,400 cm cube. And these are the relationship that you have with number of moles. Like, this is everything that you need to know about the mole concept. So that's it for today. I'll see you in the next one.